Swayam Prabha. Digital India. Educated India.
Good evening, everybody. So today we will start with the XLA approach. So previously we have seen in TensorFlow, of course, it's quite vast, and in terms of flexibility, control, and different types of approaches that we have seen. You have seen some distribution strategies, pipeline strategies, and so on. So the basic flow is write simple Python code, run on different accelerators depending on different targets that you may have, and you get optimized performance with different approaches, right? So but today we will do something extra, something bit different from the traditional flow of TensorFlow, writing codes for your models and building deep neural network models for your targets. So here, diversion is not in terms of writing the code. So the exactly same thing, whatever you have written, everything will be there. Just in terms of the compilation strategy, we will be taking a different path, and that you will see is giving you much more better performance and a lot more opportunities for optimization. So the basic TensorFlow core, if you see, so in the front end you have the TensorFlow where you will be building your models, whatever you see actually, and in the middle layer you have the existing TensorFlow core, which is written in C++, and that is being in the backend, which is providing support for your target devices like GPUs, TPUs, CPUs, and multiple devices with multiple nodes and so on. So this is the traditional TensorFlow compilation. And here, now we would like to add one more layer in this, which is the TensorFlow project, which will actually compile your TensorFlow code for your XLA devices. This is another layer of made-up device. Okay? So basically, the target for this JIT compiler will be XLA device, which is very and highly optimized device in terms of operations. So you will see that the TensorFlow, which supports maybe thousands of operations, but XLA device supports very limited number of operations, and those are very highly optimized. And that's how you will get the optimized performance for the target, which will actually the converted code or code generated by the XLA compiler will be for the target devices like CPU, GPU, and TPU, and so on. So now, what XLA is all about, that we will see in a bit. But let's look at one traditional way of writing code and interfering it, how it is going to be executed. So as you can see here, one code is there where you are actually multiplying this power of 2 into 3. So basically, you are operating on these two tensors, which is x and y, and they are defined as, let's say, with these dimensions and these shapes. And then when you are running this example, that means you are operating on x and y, how that is being written here, right? Now, if it is eager execution, it will be evaluated immediately from the Python bytecode. And if you want to optimize the performance again, so then you will would like to add one wrapper before that. But what that wrapper is, we will see. So when you are compiling this code, is essentially you can see that there are several operations. One is this power operation, one is multiply operation, one is addition operation, right? One is mean operation, and so on. So let's say 4 operations we have. And if you are compiling for your target GPU, let's say, so that means you are actually generating 4 kernels for the GPU, target GPU. So that you are seeing here. So one is for power, one is for multiplication, one is for addition, and mean, and so on. So these 4 kernels you are actually generating. So that means your code is essentially converted into your target GPU. And each operation is essentially the CUDA kernel. Okay? So basically, you underneath your CUDA C++ is being generating the code for you. So now, what is the concern here? The concern here is the number of kernels that you are generating. For this simple one-line code, you are generating 4 kernels. So imagine if you are doing one TensorFlow, let's say model training, how many number of operations that you will generate, and those many number of kernels, and they will be called again and again. You can think about the complexity that you are going to burden with the target GPU that you have. So what we want to do is that we will, of course, first optimization is you add this tf.function runtime. So what it will do, it will serialize the code. Basically, you do this wrapper, create this wrapper for add tf.function, and you define that function inside the wrapper, and that will actually generate the target computational graph. Okay, so this is your graph, as you can see: square, multiplication, addition, mean. So all these operations are making up the graph, right? And the performance gain is in terms of you are not running anymore in the Python runtime. So and you can run it anywhere then, right? You can deploy anywhere this graph. So that way you are getting some optimization with the tf.function. But it is not enough. You still have the number of operations that are actually being generated as kernels inside your CUDA. So the limitations are the function tf.function runtime is not generating new codes. Actually, essentially the codes are the primitive ones, right? And it is limited to fixed number of predefined kernels. So whatever number of kernels you have, and those kernels are from the library, and they will take the operations from the kernels and they will make this. Now, what if you can generate new optimized code on the fly, depending on the targeting in, right? So new optimized code on the fly. So there are 3 more concerns here after the graph. New code generated for new kernels. So that means you need to somehow optimize those kernels into a new kernel, into a new set of kernels. So that means you need some new compilation, right? And on the fly, JIT compilation will give you on the fly, and new code generate will be happening on the fly for your target device. So that's where this XLA compiler, which is of course still it is in experimental phase, and lots of research is going on, but the stable version is with us, so we can use that. So XLA compilation flow, flow we will see, but XLA compiler is the answer which we were talking about, the limitations of tf function. So what is happening here? The XLA compilation flow is taking one high-level optimization code, which is XLA HLO. Okay, XLA HLO. By the way, the XLA stands for Accelerated Linear Algebra. So most of the operations you are seeing inside generating one model is basically your linear algebraic operations, and optimization for these operations. So accelerated linear algebra compiler. And so for this compiler, the input for this compiler is HLO, which is high level optimized XLA. And depending on the target dependent optimizations, it will again generate another set of XLA HLO. And this will in turn get converted into a code generated for the XLA backend. And then XLA backend will actually provide the kernels for the target GPU, TPU, and CPU. So operates on the HLO IR, but how this HLO IR actually looks, and it's fast enough to not to get noticeable for large models. Okay. So now, how these optimizations are happening? Just a bit of theory we will see, because we need to learn what is happening behind the scene actually, because the way you will apply this linear algebraic compiler or XLA just-in-time compiler, there are many options to use it in many several environments, and actually where you will use that. To understand this, you need to understand a bit basics like how it is optimizing and things. So that we will talk about, and we will directly go into how we can implement this essentially in the end. So the HLO-IR, or HLO intermediate representation, whatever you call it, is basically functional in nature. Okay. Of course, there are some limitations in terms of all reduce algorithm that we have seen in the previous class. That is not collapsible, so that is actually not compilable for HLA-IR. And the number of operations that I was talking about is very, very less in contrast with the TensorFlow operations that are. So if you see total amount of TensorFlow operations, 1500 TensorFlow operations are there. In HLO-IR, you have 50 operations, around 50. And it's strictly typed. Data type plus shape should be static in nature. So now, as you can see, I was talking about these 50 operations. So that means these operations are highly optimized, which of course are a subset of these 1500 operations. And all the operations are not actually compilable in XLA. So that's where you need to know which are the operations you are going to compile to get it optimized for your target model training. So let's talk about the fusion operation here, because this is how the new operations or new kernels being generated. And the target kernels will be generated by this fusion operation. And the fusion operation is essentially drastically reducing the memory bandwidth. How? Let's say, so from this previous example, we have this multiply, add operations, and these kernels who are being generated, right? So in this multiply kernel, you can see two read operations were there, and here one read, one write, and here two read and one write operation, right? So in total, you have three read operations, two write operations to execute these two kernels. Now, if we infuse these two operations inside your compilation flow into a, let's say, fused mul add, okay, where you just have these two instead of three read operation and one write operation. Now you have two read operations and one write operation. So you can see from this very simple example of just using this multiply and add operation. Of course, they are actually based on vectors. Okay, it's not a simple multiply and addition operation. But from this simple multiply and or addition operation, you can see how many number of read and write instructions or operations we are getting reduced. And you can imagine for how many operations you can reduce in a full-fledged TensorFlow model training. So right, this is the fused operation, and this is the generated kernel that we want to generate from the XLA compilation, right? The fused operations. So if you see the IR before fusing, okay, so basically this is the IR before going into the XLA compilation flow. So this is very complex operation, all the complex computational flow. You have this complex graph. And after fusing all the operations which are actually capable of fusing, it will automatically analyze and it will fuse those operations, and you will have this fused graph. So you can see for a full-fledged training pipeline, you can fuse those operations and you can generate a new graph for that, and which will be optimized, highly optimized, and will be compatible for your target devices, as well as you can see that if you want to store the model, if you have fused operations, now how much storage efficiency you are getting in terms of storing the model itself also. So for memory constrained devices, storing the model will also be helpful using this XLA compiler. Now, what are the details and how we will use that inside a TensorFlow? Let's see that. And also we will discuss a bit of limitations that will give you a flavor of the research that is going on still. So we will see how to use that and what are the limitations in a combined. So as I was mentioning that TF function is essentially serializing the computational graph for your TensorFlow model, any TensorFlow code for that matter. And inside the JIT compile true, if you make it true, so that means you are enabling the XLA compiler. And the graph will now, whatever has been generated by this TF.function runtime will be actually compiled. That means converted into HLO IR, then all the optimizations will happen, and then you will generate the code for the target XLA device. And it performs just-in-time compilation, so it is on the fly. So how it happens? So basically, you are trying to start from the TF runtime, which is the TensorFlow TF.function runtime. You have the graph, you have the bridge. Basically, the compilation cache will actually do the bridging, because you will see in few slides that this compilation cache, which is generating the XLA HLO, actually making the bridge between the graph and the XLO HLO, that will happen in the cache, and depending on the availability of already compiled code or already code generated HLA XLA HLO, you will not be generating new codes for that. So it's highly efficient in that sense. Then you do the optimizations, code generation, and produce the executables. So that's the simple flow that we have. So now, once you have enabled the TF.function runtime as well as JIT compilation equal to true for this particular function that we were trying to, so we have now wrapped the function with the runtime, as well as we have enabled the compilation for the JIT compilation true for this particular function. So now we have generated the fused operation, which was earlier 4 operations, okay, 4 operations, 4 kernels basically, and now we have 1 kernel, and you can see that how much time you have reduced. So for this simple example, it was around 3 to 5 times, right? So yeah, on an average 4 times speed up you will get, right, for this simple fusing of operations. So now, what are the computations you want to fuse? Of course, the expensive ones, and you can fuse the entire training loop, right? You can apply the JIT compilation true for your distributed training loop, but of course, for now, it is only supporting the mirrored strategy, but we will see. And also, you can distribute, you can apply the distributed training loop with uncompilable collectives also. So some of the kernels or some of the collectives are not compilable because it has very less number of operations that we have seen, right? Around 50 operations compared to your 1500 operations in TensorFlow. So all the operations will not be compilable. So some of these operations might be uncompilable. And when you are distributing the training loop, there are ways how you can actually specify some of the part of your training strategy or distribution strategy to be compiled by the XLA and not to be by the XLA. So it's amazing. So expensive computation. So let's say we have this expensive computation as a very expensive computation function, right? We can define one function and wrap it with function runtime and enable G compilation too. As simple as that. You can have entire function fused and generated the optimized graph for that. You can have entire training loop as I was mentioning. So now entire training loop, if you want to do that, you can define one training, let's say module for that, right? And in this function, you have the training basically generating the gradients and updating the gradients and so on and so on. So the entire loop here, you are actually wrapping it with a tf function and G compilation. So that is one case. So complex operation in terms of time or expensive operations or expensive functions rather, the entire training loop you can wrap it with. Now next, the distribution strategy. If you want to distribute the training loop, that also you can do. So defining strategy, how you have to define the strategy you have seen in the previous class. And this strategy was for the mirror strategy. So we have studied several other strategies also, but for this is only applicable for the mirror strategy. And you can see that that the entire training step is wrapped with this function runtime. And when you are actually calling this training step under this strategy, so that will be essentially compiled to your XLA using XLA compiler. Now, this is the entire training loop, right? And in some distribution strategies like forward, right? So where some of the steps, let's say optimizer update, right? Gradient updates are not supported, not compilable. So what we will do in that space? So what? It's simple again. Train step essentially is the loop for your training. Calculating loss is supported in your XLA compiler, and you define one function for that compile step where you will computing the gradients. So all this backward pass, everything is happening there. Now, in this distribution strategy, applying gradients, which is the updatation stage for your parameters, is not supported. So you just keep it out of that function. And when you are defining that strategy, use that strategy with this training step, and it will automatically keep this graph out of that apply gradients pipeline. So you can see there is flexibility to define its usage as you wish. So basically, you can define which functions are going to be compiled with XLA and which functions will not. But you can use both. You can use both together inside your training pipeline. So that's very simple. But what is actually a bit difficult is to identify the blocks which will be actually compiled in XLA. Of course, there will be some blocks which will be uncompilable and some blocks which are compilable. A very naive strategy is you can apply anywhere. Okay, you can apply tf function, wrap it with any function that you want to accelerate. You do just-in-time compiler true. If that is uncompilable, that will give you an error. That's the simple way. Or you can rely on the profiler. So you can rely, like, let's say these many kernels you have, you want to fuse them. Okay, so these kernels are getting bottlenecked by the function calls and so you can use TensorFlow profiler and you can see the kernels which are getting bottlenecked. Any profiler you can use, dlprof also you can use, TensorFlow you can use. But the main thing is that you can identify many such smaller kernels. Usually the larger compiled block is actually gives you better performance in terms of XLA compilation. So you can just try it out and see what will be the best for your particular training loop that you are defining. If you are not so sure, there are flexibility as well. That is called auto clustering. So that means if you keep this environmental variable tf_xla fax equal to tf_xla auto_jeep equal to 2, which is essentially enabling the auto clustering inside your environment, that means you do not need to identify the kernels or operations to be fused and wrap it with the kernel.runtime. Of course, there is another way, which is tf.optimizer.set auto clustering. It will identify, so it will analyze the entire computational graph, and it will identify these are the operations that I want to cluster them and optimize and fuse them into XLA compile. So basically this kind of functional fusion it will do, encapsulate the entire cluster. So this kind of automatic clustering can be used. So if you want to, if you're not so sure in the beginning, just to see what are the kernels are being, let's say, optimized, converted, and fused into your optimized operations, that you can check. And you can explore the performance that gain you are achieving. But there are some glitches here because this is fully automatic. You do not know actually, right? So you can go either way. You can get very high performance or maybe very low performance, right? It's hard to predict the behavior. Now, hard to predict behavior means if you change a simple line or any even if one parameter inside your training loop, and you have enabled the auto clustering, that means each time you are running that, even if you have made a very simple change, it can make drastic change inside your target compilation. So you might get some weird performance clips for that matter. So it's better if you just know the function itself, you can just wrap it with the G compilation tool and use the predicted behavior. Whatever you can have, you have the optimized performance for this particular function, or you will get error if it's not compilable. Now, not compilable means, let's say you are loading some data from your resource, maybe a local disk or remote sources, and in the process of loading, you are actually, let's say, decoding something or maybe applying some image processing, which is let's say image encoding decoding, which is not particularly supported in GPUs or maybe XLA target device, right? So in that case, XLA will return you an error, and that will actually be offloaded to the CPU part, right? So it's automated. So you just see the error and change your JIT compilation to function wrapper. But anyway, I mean, you get some predictable behavior that it will get this kind of output. Uh, but there are some limitations that you need to know, because you need to know some unsupported operations, as I was mentioning, that image encoding decoding, which is not supported in XLA compilation. And recompilation will happen every time you change the shifts, because it is actually based on the cache-based IR generation. So we will see one example, such example, and that will actually reduce the performance that you want to achieve. Recompilation will happen also if you have some constant changes. So recompilation means, so it's on the fly compilation. So recompilation means it will take a bit's time if you are changing something and recompiling. One such example that we will see here. Let's say you have there may be unsupported operations. Maybe many of them, image decoding ops, are not supported, and so you will get runtime exception, as I was mentioning, that you will get an error, and you can trace that wherever it is happening, and you can change that for your private XLA compilation. So you will get some error like this. So you will just return that this is the error, and this is the reference. Basically, the image decode that you are using to process this data or while loading the data. Okay. So this process you wanted to optimize with this TF function runtime, and this operation is not supported. It will give an error, and you know that this is not supported. And if you don't know, of course, you will get a list of operations that is supported in TensorFlow.org, and you will go to the XLA and what are the HLO optimizer or IR, what are the operations that are uh, supported that you can get a list from. Well, so now when what are the cases when you will get some performance glitches? When you have static shapes change. So basically, if you see that uh, basically this function, this cumulative sum, okay, and this function is targeting these vectors, right, or these tensors, and now you have the shapes of these tensors 10 10 10 10 in the next compilation also, or next competition graph. You can see it's the same dimension 10 10 10 10. So that means it will not again compile for this particular section. It will use already cached IR generated, and it will generate the code for it because it has all the dimensions same. It has, because it was typed strictly typed, the XLA is strictly typed, and shaped also must be static. So if you have the same shapes, your code will not be recompiled. And if you have changed, so basically in the third operation, you can see once the number of ones are getting increased here, the bound is getting increased. So that means it is no longer supported. The previous uh, IR is no longer supported, and you need to generate new IR. So you will again recompile. So basically, it will take some more time. You expected that it will happen because all the things are supported. So basically, yes, supported, compilable, but due to this shape changes inside your code section, it is taking actually a bit of more time because of recompilation. Such another recompilation scenario may appear if you have constant argument changes. Basically, you can see that in this function, you have two arguments, one tensor size of 10 10 and 0, 10 10 0. So again, so for this IR is there in the cache hit again, so it will not generate. And for that, you'll see that one more change is there in the constant, and it needs recompilation. So basically, so such functions where we are actually comparing, let's say, which is the maximum between these given the tensor here, okay, A, and so you are trying to figure it out, what are the things happening because of which we are getting performance degradation. That is because your something might be wrong with different constant changes inside your code. So these are the limitations that you can see. So of course, researchers are trying to figure it out how to actually pipeline these transformations and make predictions like what can come in the next, and do introduce some kind of dynamic nature, because that is very, very important. So some research is going on in towards that direction. Now you have the flexibility to inspect your code, what is happening actually. Uh, you can enable this flag, okay? So you can inspect part of the generated HL, basically the generated graph or infused graph that you have after the optimization part of the graph that is available. So both you can inspect and see what are the things going on inside your code for your target model. Basically, this is one example where you can apply this. So basically here defining one function which is wrapped in the function runtime with JIT compile true, and we are generating. So basically here we are generating the HLO for that particular. Okay, so if dot experimental get compiler IR for this XY we are generating. So you will have XY tensor or whatever, and it will actually print the generated HLO. To see the optimizations, what are the optimizations that XLA has performed, you can call this function f dot. So f is your function which is being wrapped by the function runtime with JIT compile true. So f dot experimental get compiler ir xy stage equal to optimized HLO, because there are several stages. You want to see optimized HLO or what are the optimizations happen. Or you can print the graph into a dot format, okay, and you can use graph viz or graph viz converter from, let's say, a dot file to JPEG, and you want to see the graph generated, right? So if dot experimental get compiler here will generate the dot file for your target or optimized code computational graph. So that's about it, and we will use that and inside with all the pipelines that we have discussed, right? So starting from your data pipeline with TFDS or TF.data, then you have different distribution strategies. Then you have mixed precision. You have XLA compilation flow. So you can see that there are many things that you can apply to get much more enhanced performance for your target model. So we will see all together in one example, but in conclusion, so we have the option for TF.function wrapper with JIT compiler true, annotate with that for the particular function, and you will get great performance with that. Basically, in general case, you will get for, of course, for a heavy model, we'll show you that applying randomly with very small models, it might get you bad results even, okay, sometimes. Ideally, you will compile the largest cluster for that, and so that's where you will get the best performance out of it. So let's jump into the demo session where we will explore more about that.